In previous videos, we've been studying velocity with this equation, v is equal to d over t. And that's fine, we can do lots of things with that formula, but it only applies to uniform motion. This doesn't apply to that many scenarios. We're kind of limited by it because uniform motion means going the same speed in the same direction, not changing speed or direction, but there's lots of times where we do have something changing speed or changing direction. So we can no longer use this formula for those scenarios. Changing speed or direction is not uniform motion. It's called non-uniform motion or accelerated motion. So in this video, we're going to discuss how to calculate questions with acceleration. Okay, so starting with our definition, acceleration is defined as a change in velocity. Velocity is what we looked at before. It's measuring how fast. It's also the vector quantity for how fast. So it takes into account how fast and what direction we're going. That's what velocity was. So if we are changing our velocity, we're either changing how fast we're going or we're changing the direction that we're going. Okay. Acceleration, because it's looking at the change in velocity, a vector. Acceleration is also a vector, and we're going to measure it in meters per second squared. Meters per second squared, kind of a weird unit. Let's take a look at what it means by looking at an object falling. An object falling is a good example of acceleration. The acceleration of gravity is very common for types of questions we have in physics. Okay, so to see what's happening on the side here, let's say that we took a snapshot or a picture for every second that it was falling. Okay, so we got 0 seconds, 1, 2, and then 3 seconds down at the bottom. Then if I was going to show its velocity, how fast it was going at each section, we could get those on the side here. We have 0 meters per second, 9.8, 19.6, and then 29.4 right before it hits the ground at the bottom. Okay, when we analyze this motion, we can see that the gaps in between keep going up by 9.8 meters per second each time. It went from 0 to 9.8, 9.8 to 19.6, and then to 29.4. The jump or the increase is always adding 9.8. So that's the acceleration. It's speeding up by 9.8 meters per second every second. So that rate of 9.8 meters per second every second is how we describe our acceleration. Now, instead of saying meters per second, we just put those per seconds together and describe it as 9.8 meters per second squared. It's basically just like saying seconds twice. So meters per second squared. And that's looking at the change in speed, but we could also look at the change in direction. So this would be if we have a car maybe driving up, and then it's going to be going at 10 meters per second the whole time, but it changes its direction and drives down kind of over here. This also is called acceleration. It's centripetal acceleration, and that's what we're going to look at more in Chapter 5. So we'll see more of that coming up later on. So today we're going to look at how to solve for questions where it's accelerating or speeding up or slowing down in one direction. So how we're going to solve those, the challenge is there's a lot of equations because there's actually quite a few variables involved in all these equations. All the equations usually given to you on a data sheet, but we're going to go through each one and kind of how you pick the right equation. So we're going to introduce you to 5 acceleration equations. For uniform motion, there was just one. We unfortunately have to know how to use 5 for acceleration, but the process actually isn't too bad. We're going to try and make it as easy as possible for you to understand these 5. Starting with the first one, our first one is acceleration is equal to velocity final minus velocity initial divided by time. It's basically the definition of acceleration, the change in velocity, final minus initial, divided by time. And there's our acceleration in meters per second squared. Okay, so let's plug into an equation and a problem to see how we use this one. Let's say that a car accelerates from 15 meters per second to 20 meters per second in 3 seconds. How do we solve for its acceleration? We'll start with our formula here and plug in. At the end, we're going 20 meters per second. At the start, initial, we were going 15 meters per second over 3 seconds. Plug in our values, and we get a nice answer of 1.7 meters per second squared. Okay, so not bad to plug into that one. Didn't have to do any rearranging. You could if the question looked a bit different, but we'll get into those in a minute as well. The other note I want to make here, though, is this is assuming that we are going at a constant acceleration. All our formulas here are going to assume that the rate that we're speeding up is going to stay consistent. That's not super applicable. Often, for example, cars going from 0 to 100, they can accelerate really fast at the beginning, but at the end, it's hard to speed up when you're already going fast. So it does change in real life for a lot of scenarios, but in this case, we will assume always constant acceleration. And that's kind of why I chose this example. Speeding up from 15 to 20 isn't that difficult, especially in 3 seconds. We're giving it some time. So it's reasonable that this could have a constant acceleration, and we calculated that constant acceleration to be 1.7 meters per second squared. So there's the first equation. What are the other ones going to look like? Well, first, the purpose of the other ones is to solve for other variables. So what if we know the car's accelerating, we know it's starting and ending speed, but we want to know how far down the road does it take for it to speed up from 15 to 20 meters per second. That introduces us to the second equation here, which is d is equal to half our same vf plus vi, that's velocity initial and final, as we saw from before, multiplied by time. Okay, let's take a look how that one would apply here. So how far did it travel in this time? We're going to start with our second acceleration equation, plug in vi, vf, and t for this one, and we get a value of 53 meters. That means during this acceleration, the car's traveled 53 meters down the road. So hopefully from these two examples, you can see plugging into them is not that bad. The challenge is kind of knowing which equation to use. So I'm going to introduce the next 3 pretty quick. How you get to the next 3, they're all kind of combinations of these two, just rearranged and substituted in. You'll never have to do that though, because it's on the data sheet. So I'm just going to introduce those to you kind of quickly here, and then we'll talk about how you pick which one to use. So number 3 looks like this. We have d is equal to vit plus half at squared. The fourth one's almost identical, just has vf and a minus. D is equal to vf squared minus half at. And our last one here, vf squared equals vi squared plus 2ad. Okay, I went through them quick because they're on your data sheet. But the big question is, how do you know which one to pick? You see all of these equations, you see them on your data sheet, and you're probably feeling a little bit like this, going, oh my gosh, I'm overwhelmed with all these formulas. Which one am I going to pick? Well, it's actually not too hard of a process. Let's show you how to pick the equation so you can solve usually for what you're trying to figure out in just one step. So let's take a look at that. Okay, so this is how I would set up my page to pick the correct equation. Now, I wouldn't write down each formula. Those are on your data sheet. So you're looking at your formula sheet, and I would write down VI, VF, A, T, and D. Now, I listed all the variables here. You do notice that I don't have V is equal to D over T. That was from the last lesson, the last video on uniform motion. And as soon as we notice the question is talking about accelerated, something's falling, a car is speeding up, we don't want to use V is equal to D over T. Okay, so we're only going to look at these 5 for those. So how we're going to pick, for any question, we're going to have some pieces of information here and be missing other parts. So let's say that we have VI, VF, and D. The question tells us those 3 variables. It's really common for us to have information about 3 of them, but we're missing 2. There's 2 that we don't know anything about. Okay. So what we're going to do from here is, well, the question's only going to be asking for 1. It's going to be asking you for what's the acceleration or what's the time. So let's say that the question says, what was the time that it took to undergo this acceleration? What that shows me that I listed my variables is that I care about the information that I have, and the one I'm trying to solve for, I don't care about the number for acceleration. That one is not important. I'm not trying to solve for it, and I don't know what it is. So now here's the key. When you look at the list of formulas, all of them have acceleration except 1. All of them have acceleration except 1. And once I find the one that doesn't, that's the one that I'm going to use. Because I don't care about that value. I don't want to find it, and I can't use it because I don't know the value. So the one without that number, the acceleration, is the one we're going to pick. Use that same process based off whatever you have and whatever you're trying to solve for, and you'll always pick the right one. For a real life example of how to pick the right equation and solve for some real data, let's take a look at this cliff diving video and try to figure out how tall the cliff is. Okay, pretty impressive video. The guy was in the air for a long time. It registered at the bottom, said 3.1 seconds. As you can see in the video, a huge cliff. I can never do anything like that, so that's why I had to source his video. Very impressive to whoever that was. Very good job, and really glad you gave us the time so we can do some calculations here. And we're going to see if with basically just that information, the time that he fell, if we can solve for how high the cliff was. Okay, so let's list the information we know. And I'm going to start up the top with VI. And maybe he jumped a tiny bit at the start, but he basically kind of tipped off of it. So I'm going to assume that he started with initial velocity of 0. A bit of an assumption, but it looked like basically just a tiny little hop, mostly just fell from 0. Okay, next it comes to VF. How fast he hit the water? I have no idea. I'm going to put a question mark. Don't know how fast that was. Acceleration might seem like we don't know it, but he accelerated due to gravity, and on your data sheet, it tells you the acceleration of gravity is negative 9.81 meters per second squared. For anything that's falling, we can use 9.81 meters per second squared. So we know that value. The distance, that's what I'm trying to solve for. And the time, fortunately, the video gave the 3.10 seconds. Okay, so this is just like our common scenario where they've given us 3 pieces of information. I don't know 2. So next thing is to find what we're trying to solve for, which is D, which means I don't care about VF. I don't have that information. I'm not trying to solve for that information. I don't want VF. So I'm going to look through the equations and pick the one that does not have VF, and it's this third one here. D is equal to VIT plus half AT squared. So let's work with that equation now. I set it up. Fortunately, it's already rearranged for D. I don't have to change that at all. And so I'm going to plug into my values, but just before I do, we can actually make this a little bit simpler. The velocity initial, VI is 0, and it's 0 times time. So anything, whatever the time is, in this case it's 3.1, but whatever the time was, something times 0 just gives you 0. And we're adding that term, so we're just adding 0. That shouldn't affect it at all. So we can just cross out the VIT. It's going to make our solution a little bit easier. Now, if you plugged it in, that's fine. But later on, we're going to see that the ability to do that is important for when we look at projectiles. Anyway, continuing with this example, now I have D is equal to half negative 9.81. That's telling me it's accelerating down times 3.10 squared. And I get a distance of negative 47 meters. Negative because he fell down. Before we move on to the next example, let's just take a minute to appreciate how freaking high this cliff is. He fell 47 meters. 47 meters is huge. And we don't really have a context for this because I imagine a meter stick 47 times. Let's help get this in context. An Olympic diving board is 10 meters tall, and he fell 47, nearly 5 times an Olympic diving board. So I'll shrink it down, put 5 up there. That's about how high he fell. 5 times an Olympic diving board. To put even more context, this is the same as about a 15-story building. A story in a building is about 3 meters. So we divide it and we get just over 15 stories is how far he fell. So very impressive dive, and I didn't play the rest of the video, but in case you're wondering, the diver is completely okay. He's fine. He did the jump well, and no one was hurt in this video. So he's very impressive and doing well still. Let's do one more example. I don't have a video for this one, but just made up a number. Let's say someone jumps off a cliff. This is a separate example. So someone else jumps off this cliff and they hit the water at 50 kilometers per hour. Again, safely. They do the dive well and they land safely. They're not hurt. And they hit at 50 kilometers per hour. 50 kilometers per hour, pretty fast. It's the speed that cars, the posted speed limit that cars go in town often, 50 kilometers per hour. So pretty quickly. And we're trying to find how tall would this cliff be to hit the water at 50 kilometers per hour. Well, our same process lists VI, VF, AT, and D. And VI is still going to say 0, not jumping up really high, basically just falling off the cliff. VF is 50 kilometers per hour. However, I'm not actually going to put the number 50 because units are important. My acceleration in meters per second squared means I need meters and seconds for this. So not kilometers an hour. So we're going to convert that by dividing by 3.6 and we get 13.8 repeating, but let's say 13.89. So important to have that in meters per second. Okay. Acceleration, 9.81 meters per second squared. We can see there, that's why we need the velocity in meters per second. The acceleration is meters per second squared. So I got to keep those units consistent. I don't know D and I don't know T in this example. So again, really common, 3 trying to solve for one other one. Okay, let's look at what we're trying to solve for. The question is asking for D, displacement. So in this case, I actually don't care about time. I don't have it. I'm not solving for it. I want the equation that does not mention time. And that is our last one at the bottom, the fifth acceleration or kinematic equation, whatever you want to call it. Vf squared is equal to Vi squared plus 2AD. So using that formula, I wanted to do this example because it shows sometimes you have to do a rearrangement. Sometimes it just doesn't equal what you're solving for. In this case, we have to rearrange it to solve for D. So look at the rearrangement here. I'll just bring up my pen. I want to solve for D right here. So I got to move Vi to an A. So we'll do reverse order bed mass, which means brackets, exponents, division, multiplication, addition, subtraction. So first I'll look at my addition, subtraction. Okay, so it's Vi squared plus this term. So I'm going to get this term by itself, minus Vi squared, and move it to the other side. Okay, now I'm looking here. I don't have any more addition, subtraction. I just have multiplication and division. So I'll divide by my 2a, a little bit messy there, but divide by 2a to get d by itself. Another important part, I'm going to have the brackets down here because I want to divide by that as a whole. If you forget those brackets, it might give you an incorrect answer. So make sure to bracket those numbers. But now we got d by itself. Let's plug into the equation. My Vf squared minus Vi, I didn't really have to include this. I could have just cropped that out because I knew Vi was 0. But this is when I plugged it in, still going to work. Divided by 2, negative 9.81 because we're going down. Again, brackets around all of that, and I get an answer of 9.8 meters is how far they would have fallen if they hit the water at 50 kilometers per hour. Now, as much as we want to calculate the right values, which we did, we want to think about what this means, and we realize 9.8 meters, that's basically 10 meters, which is the same as the Olympic diving pool we looked at before. So when these Olympic divers do all their dives and their flips and twirls, everything like that, they hit the water at approximately 50 kilometers per hour. If they were like 0.2 meters higher, 20 centimeters higher, it'd be 50 kilometers per hour. So they're basically hitting it at 50 kilometers per hour every time. That's pretty risky doing this jump with all those spins. So it shows that Olympic diving to be quite impressive. And also, if they hit it at 50 kilometers per hour, imagine the guy on the 47-meter clip. He must have hit it incredibly fast. Has to be perfect with his landing so that he wasn't hurt, which in case he was not hurt, which is good. You could calculate that velocity, but that's going to be it for this video. So I'm going to end it right there. I hope that helped you with understanding and calculating acceleration in all types of scenarios. Thank you so much for watching, and I will see you in the next video.